Hello everyone, I'm Kashmala Rehman,
I'm Maria Galkin.
I'm Benjamin Swanti.
I'm Sunada-Wong.
I'm Harvey, Wang.
and this is a hygiene monitoring system. Before we begin, I'd like to give an outline of what we're presenting today. We'll start with the background, where we'll define our purpose and give you some prior knowledge on our topic. Then we'll move into the methods, where you'll learn about the key networks we used and the machinery. Then we'll move into the procedure, where we'll define all the key steps we took to accomplish our system. And in the results, you'll see some data and some graphs which determine the success of our project. And in the conclusions, you'll see some future advancements, the significance of our findings, and some applications. And lastly, there'll be a Q&A session where you'll get to ask us some questions and we'll happily answer them. Needless to say, hand hygiene is imperative in all settings, but especially in a healthcare environment. And so we developed a hygiene monitoring system which would detect whether the correct hand hygiene protocol is being followed. And as a result, we hope to increase the healthcare workers' compliance to the hand washing protocol and decrease the transmission of germs from staff to patients. Here's some background on our topic. So the World Health Organization recommends washing your hands for at least 40 to 60 seconds. And in that time period, there are 6 motions that should be performed, and in no specific order. So please join us as we guide you through the motions. This is called simple press, and this gets the palms of the hands. This is roof, and it gets between the fingers. This is called web, which is done for both the left and the right hand. It gets between the fingers and the back of the hands. This is mortar and pestle, which gets the fingernails, the fingertips, and the palms, and it's also done for both hands. This is link, which gets the knuckles, also done for both hands. And lastly, this is thumbs, also done for both hands. Furthermore, the World Health Organization recommends 5 moments in which a healthcare professional should wash their hands. The first is before touching a patient. The second is before a clean or aseptic procedure, such as changing a patient's clothes. The third is after a body risk fluid exposure, such as taking a blood test. The fourth is after touching a patient, and the 5 is after touching a patient's surroundings. And this means even if a doctor simply walks in and does nothing except touching the patient's bed and leaves, to abide by the hand washing protocol, he or she should wash their hands. And now these instances might seem obvious, but surprisingly, less than 40% of healthcare workers abide by this protocol. And as a result, in developed countries, 5 to 15% of healthcare infection impact 5 to 15% of hospitalized patients and 9 to 37% of patients in intensive care units. When the correct hand washing protocol is not followed, otherwise avoidable infections can make their way from the healthcare setting into populations around the world. And that is why we developed the hand hygiene monitoring system, so we could prevent this problem.
Now we will be going over the methods we used for our hygiene monitoring system. In order to accomplish the task of recognizing the 6 hand poses recommended by the World Health Organization, we needed to develop an image classification system. In our project, we used a neural network because of its ability to recognize complex patterns in images. So a neural network is a computer model that's based on the human brain. As you can see on the diagram on the left, a neural network is comprised of layers of neurons. Each neuron takes an input, which is a number between 0 and 1, and transmits it to the neurons in the layer in front of it. In contrast, a convolutional neural network has the addition of convolutional layers. The idea of a convolutional layer is to be able to recognize spatial features in an image by applying a filter that moves across the image and captures a specific feature. As you can see in this diagram, the filter is the orange box that moves across the filter. And the effective thing about a convolutional neural network is that it is translation independent. Because that filter is applied across the whole image, it doesn't matter whether your hand is on the left or the right side of the screen, it should still be able to recognize that same feature. Now, one problem with a simple convolutional neural network is that as the depth of the neural network is increased, the training becomes less effective, and that's because of the problem of vanishing gradients. In order to solve this problem, you introduce residual layers, which are represented in the diagram on the right. A residual layer introduces a shortcut connection between layers of the neural network in order to increase the connectivity between the earliest layers of the neural network and the final output layer, and increase the efficacy of training. In our project, we used ResNet 18, which stands for Residual Network, and it has 18 layers. We'll be talking more about this network later in the presentation. And finally, the third technique that we used in our project was transfer learning. And this is a technique used in machine learning where a model is first trained on one set of data and then retrained on a different set of data. The purpose of this is to increase the end accuracy of the model and also decrease the training time. As you can see in this diagram on the right, the model on the top was trained on task A and was retrained on task B. The way this is done is the earliest layers of the network are kept constant, while the final layers which perform the highest level feature recognition are retrained. And here is a diagram of our project workflow. So our project begins on the left with the scene. In this case, it would be a subject washing their hands. This scene is captured by our AWS Deep Lens, which is a camera and a computer all combined into one environment that is used often by machine learning developers. The AWS Deep Lens accesses our machine learning model through a Lambda function and outputs the prediction of that model to our project stream, which was a monitor that allows the user to see the prediction of the model. Now we will be going over the procedure.
So our procedure consisted of 4 main steps. Number 1, we had data collection. Number 2, model training. Number 3, validation and refinement. And number 4, deployment to the Deep Lens camera. So first of all, our initial data collection consisted of over 30 minutes of hand washing footage. So each of us did the 10 poses, left and right hands, and we were left with 30 minutes of hand washing footage that we used OpenCV to extract frames from. So we extracted three frames per second, and we were left with over 5,000 images. And from these images, there were some that were blurry or our hands weren't completely in the frame. So we took out these images that weren't suitable for training, and we put the remaining pictures into an AWS S3 bucket, which is an online storage service provided by AWS that allows us to easily access this data via the cloud. Next, we were ready to train our first model, and as Warren mentioned, we used a ResNet 18 pre-trained model, and this was actually trained on over 1 million images from an ImageNet database, and it could classify images such as dogs, cats, trees, cars, etc. And in order to utilize this model first, we had to prepare our data. So we labeled the images based on the different hand poses they were representing, and then we separated them into training sets and validation sets. And the training set comprised of 2,500 images that would be used to train the model, and the remaining would be used to test the model once it was complete in the validation set. And then we were ready to modify our model, so we changed the last couple of layers of the model, as Warren mentioned, for transfer learning, and this would allow us to classify the images into the different hand poses as we needed for our project. So next, we were ready to validate our model once it was done training, and we initially used the footage from just the 5 of us, and after we completed a batch transform and inference, which was an efficient way of receiving the test results in one go, we then introduced new hand washing footage from 5 additional subjects that the model had never seen before. And once we performed yet another validation set, and once we realized that we needed to retrain our model to improve our performance, we added 1,500 additional frames from these 5 new subjects into an updated training set, and then retrained the model and ran another validation set. And then once we were satisfied with these results, we were ready to deploy to the camera. And when we're deploying to the camera, it looks like, there should be a video here, sorry. So in order to deploy to the camera, we've had to create a project that comprised of an inference, a Lambda function, and also a path to the model that we just created in our training job. And so what happens is, as there's live video input coming in from the camera, the camera sends this footage to the inference function that acts as the middleman between the model and the input video. And then what happens is, using the Lambda function that we wrote, we can create an interface on the display on the monitor, and then it'll show the real-time inferences at the top of the screen. And on the right side, it has the percentage confidences for each of the different poses. So that shows you what the model believes is going on within the camera frame. And it looks like it's not working right now, but you can stop by later at our booth during the demo session and you can see it working in real time.
All right, thank you, Harvey. So now we're going to get into the results of our project. So I'd like to reiterate before we begin that the purpose of our project was to develop a system that can detect proper hand washing. So in order to determine the success of our project, we had to get a system accuracy from the model. So as you can see here in this chart shows the accuracy of the different hand washing positions. So to calculate this accuracy, what we did was we took the number of images that were classified correctly by the batch transform, as Harvey had mentioned during the procedure, and divided that by the total number of images in the batch transform. So as you can see from our original validation set, which consisted of images that were part of the original training set, so those were the original 5 test subjects, all of the categories returned an accuracy of higher than 75%, which is successful for this particular machine learning task. And then here you can see a graph that shows the distribution of the different classifications of the images. So if I were to read this graph, you can see the actual category on the x-axis, the predicted category on the y-axis, and this shows the different distributions. So if I wanted to see how many of the images were labeled as web right from the web right category, I would look right here at this bar. So as you can see from this graph, it's pretty clear that most of the images in the original training set were labeled with the correct classification. But because this is a machine learning task, we had to run another validation set to confirm our results. So once again, we added images from 5 new test subjects that the model had never seen before, and the accuracies are shown here in this chart. The accuracies were much lower, particularly with some positions such as roof and simple press. And this can be attributed partly to the idea that these images, or these positions rather, are very similar in their appearance, but also the idea that these images were new. They had different lighting, slightly different backgrounds, although they all had white backgrounds. The hands were of different size, curvature, and skin color, and the model had never seen them before. So this was a cue to retrain the model. I'll show the distributions here. Again, it was much more varied, with some of the images being classified under the wrong category, particularly with the link and thumb motions. So after we retrained the model and we added much more images to the training set, you can see that the accuracies are again much higher, above 75% for all of the categories. And the average accuracy that was returned by the model, the retrained model, was 88%, which is successful, and that was the cue to actually deploy the model so we can get a real-time inference. And then here again, you can see the distributions are less varied, and most of the images are classified under the correct category.
Thank you, Maria. Now let's go on to our conclusion. So first I want to discuss the significance of our result. Again, as Maria said, we were successful in retraining our model. Initially, we made the model, then we used validation data and had insignificant results. And therefore, we created a new model and got significant result, where accurately predicted the curvature and moment of our hand washing motion and can do it in real-time motion, meaning we get accurate result on the fly and use to monitor hand washing. As they had multiple applications. For example, in the healthcare industry, medical professionals must wash their hands in order to ensure that the patient is healthy. Therefore, if we monitor hand washing system, we're able to ensure that medical professionals wash their hands successfully and are able to provide patients with the best care possible without giving them further infection. We can also see that in developing countries that don't have the same medical care as the United States. As we implement these systems, we increase compliance with the healthcare system, and therefore we encourage the medical professionals to have the same to wash their hands and ensure success and a low mortality rate. And finally, we see that in the food service industry. Within the food service industry, employees must wash their hands in order to ensure that the food given to customers is safe and healthy to eat. Therefore, by monitoring these systems, we ensure that they are successful. Finally, we have a lot of improvements we would like to make on our project. First of all, is our hand detection system. We were limited in our project on using a white background with specific lighting for our project in order to ensure that we get results. However, in future implement, if we can eliminate the background and simply focus on the curvatures of the hand in order to make sure we get a full image, we can increase the accuracy of our project. Now, we would like to see a larger database. We were limited based on our population of GTAC 2019. However, if we increase the population to people outside the data, such as in New Jersey and the United States, we're able to have a larger population and more photos to use to retrain the model, and therefore have a greater probability of success. And finally, what happens as a neural network might be possible under increase our accuracy. For example, as we use RedNet 18, we could also have done MobileNet version 6, where as you see more lightweight, meaning more user-friendly and possible. And also, it has a greater accuracy, so therefore it might have been more accessible for us and to get greater results. And finally, we would like to thank everyone here on this list for all the help they have sent. This includes Mr. Andrew Page, Carolyn Jeon, Helen Sadid, Michael Hidden, Dean Antoine, Nathan Hobbs, and Al Springer, including all our content. We couldn't have done this project without you. Thank you for your time. Thank you for your time, and feel free to ask any questions.
Yeah, so one of the things that we considered as a potential improvement to our system was the addition of isolating only the hand in the image so that the model doesn't get confused by the backgrounds. And that's something that could be done with like k-means, the k-means algorithm. I think they did that in last year's paper, but it's something that could definitely be added to the project.
This is really nice work. Just wondering if you consider to use a time series of different images in sequence so you can enhance your accuracy.
Yeah. Do you want to say?
Oh, we consider that initially. However, because of how the AWS works in RedNet, we actually needed to put it up into frame rather than specific series. But if we did series, we can also calculate with the motion. But due to the limitation of the device, we weren't able to make that possible. And
another thing I wanted to add was recurrent neural networks are another type of neural network, which the advantage of those is they store memory of previous inputs that were given to the model, and that would accomplish a similar task as a video, where it would be able to recognize like motions as opposed to just the still frames, which could be applied if this project were to be done in the future.
So you actually mentioned you have 2,500 images in the original training set, yes, for 5 people, yeah?
Yeah.
How long did it take to collect and label this data?
Data collection, it really didn't take too long to collect. It was just the 30 minutes of recording the videos. And in terms of labeling and actually training the data, all of that went really smoothly and quickly. We were able to train our model within less than 20 minutes. It's mainly because of AWS's cloud computing capabilities. They were able to achieve a level of speed and performance that we can't really achieve locally on our computers, which is why we were so happy to be able to access these cloud services provided by Amazon. So it was a relatively quick process thanks to the power of Amazon's cloud computing service.
How many images did you add to the second training set?
We added 1,500 images, and so in total our training set was 4,000 images for the second model.
Did you have any negative examples from this? Motion is not correct hand washing or not hand washing at all?
No, we did not. But that could be something we could add in the future project. Last question. There.
Yeah, I wanted to know in the data collection when you were actually collecting the frames and the imaging, was there any difference between different skin colors and how it influenced the results? Like did the camera pick up certain shades of skin, better than others, and that influenced the results?
Initially we were going to deal with skin color bias, but due to complicated reasons, we weren't able to continue with that goal. but it is a consideration to keep in mind for the future. And throughout the result, throughout our validation, we did get students of different skin tone in our validation set and our retweeting model. So we were able to successfully have a unique platform of people of different skin colors, and it can actually detect hand of skin color provided.
I think that's all the time we have. Thank you for listening.